compounds with carbon. The element of 16 compounds with carbon like
mass spectrograph is an instrument applied to separate different particles from electric and magnetic fields over the same region of the earth to separate iron oxygen from the mass spectrograph include oxide
element of group 16 form several types of oxide which are monoxide, dioxide, and television is a individual masses after completing mass or dioxide sulfur dioxide. This is a stable colorless gas. Stable colorless gas. Stable colorless gas gas having stable colorless gas having odor of burning sulfur. Odor implies odor of burning by sulfur. Odor of burning sulfur. Next we go. This is will get it sulfur monoxide formed by classic electric charge to magnetic discharge. That is by R1 minus created by the electric discharge to sulfur monoxide. As high in the high is very small. Other monoxides are formed by corresponding dioxide. Okay, and study about the ozone of the in our library table from that also by the okay, what the difference is the same atomic proton number Z and what different atomic mass the isotope of an electric contain the same number of protons but different number of electrons. For example, oxygen has two isotopes, 8O16 and 8O17. Hydrogen has three isotopes, 8O16, 8O17. Hydrogen has three isotopes. One H1, hydrogen has three isotopes, H1 and then one H1, one H1 that is known as hydrogen, and one one H2 that is known as deuterium, and third is tritium, one H3 tritium. Neon has two isotopes. Neon has two isotopes, 10 neon,
what is working of mass spectro
and
okay,
22
working
neon, 10. Okay, chlorine has two
mass
isotopes,
spectrograph. Okay,
the positive ion 17,
the positive ion which
37
enter the chamber D. The
I
positive ion which
possess
enter the chamber
about
D, enter the chamber
297
D,
different
are subjected
isographs
to a
are
strong
known.
magnetic field of intensity
And
V2. Strong magnetic field intensity
that's 5 equal to 1 minus 5 square by factorial 2, 5 square by factorial
acting
2,
on each
and
ion
plus pi by pi to the power 4 by factorial 4, and cos phi equal to 1 minus 5 square by factorial 2, and
ion
pi to the power 4 by factorial 4,
radial spectral are given by
1 minus pi square by 2 approximately
square by
approximately then
R
equal to 2 r
mv
1
by
minus
V2
1 minus
V2
1 minus pi square by
Okay.
2, that
Then,
is r pi square.
E by
And pi is small
capital M
as
equal to
pi
E by
is small
V2
pi is
R
small
is equal to
then
E by
pi square
V1
is extremely
R.
small. Is extremely
E by
extremely
V2
extremely
Okay.
small,
Where
extremely
V
small,
E by
and the width of the
V1
focusing
V equal to E by
and
V1
and the width and the width
as
of the
V1
focusing of the
V1 and V2 are
focusing
constant
width of the focusing PQ is very small. PQ is very
V1
small,
and
very
V2
small. PQ
are
is
constant.
very small. All the particles having same momentum and the charge will be
directly
focusing
proportional to
between
1 by
R. All the particles
by
all the
M is inversely proportional
all the
to
particles
R.
having same
After
momentum,
describing the
having-
semicircle
having
path,
same
the ions
momentum,
strikes a
same
photographic
momentum, having
Okay?
same momentum,
Photographic plate.
having
Determination of
momentum. All the particles having same momentum and
mass.
charge will
Okay?
be focused. Momentum
Determination
and
of mass.
charge
1 minute.
and the charge will be focused. Will be focused.
Determination of mass.
Charge will be focused
Determination
between PQ.
Determination of
P
of
Q.
mass. Determination
The particles having
mass.
different
Okay?
values of momentum.
Determination of mass. Okay?
The particles
Determination of mass.
having
If E is
the
the
particles
same for all ions,
the particles having different
small
values of
atomic
momentum.
charge is the same.
Different
Same
values
is the
values
same
of
for
momentum.
all ions. All
Momentum
ions.
and charge will
Then
be
capital M is directly
and the
proportional to
charge
R.
and the
Thus,
charge
we get a
will be
linear mass
charge
scale on the
will be
photographic plate.
focused
The
at
ion of different mass will
focused
traverse path of
focused
different
at
different
focused
radii
at
and describe the
points.
photographic plate at
Different-
different points,
different
thereby giving a
points.
typical mass
different
spectrum.
points.
The
Therefore,
method is very
useful in
structured.
separating.
The
Therefore, this
method is very
useful
as the
in
mass
separating.
scale is
Very
linear.
useful in separating. Therefore,
The
this method is
method-
very useful in separating the
method
isotrophs.
is
Separating the isotrophs.
very
Therefore, this
accurate.
method is very useful in separating the
Very
isotrophs.
accurate.
Okay.
As
And next heading,
the
mass
mass
spectrograph.
as
Mass
mass scale
spectrograph.
is linear. Mass scale is linear. Mass scale is linear. Okay. Next point. No change in kinetic energy of a charged particle in a magnetic field. No change in kinetic. No change in kinetic energy. No change in kinetic energy of a charged particles. No change in kinetic energy of a charged particles in a magnetic field. When a charged particle is having a charge q, and velocity small v, kinetic energy 1 by 2 mv square, enters a magnetic field of intensity b perpendicular to its path, the force acting on the charged particles and the direction of the magnetic field, the charged particles will therefore move in a circular path of radius r given by VQV equal to mv square by r. Okay. R equal to small r equal to mv by bq. Okay. As the force due to the magnetic field acts in direction at right angles to a direction of motion, the force will only change the direction but will not be able to bring about a change in the magnitude of the velocity. The kinetic energy of the particles will therefore remain unchanged. The force due to magnetic field will only make the charged particles move along a circular path with the same velocity and therefore the same kinetic energy. Okay. No change in kinetic energy of a charged particles in a magnetic field. When a charged particle is having a charge q, and the velocity small v, kinetic energy k equal to 1 by 2 mv square, enters a magnetic field of intensity b, perpendicular to its path, the force acting on the charged particles and the direction of the magnetic field, the charged particles will therefore move in a circular path of radius small r, then VQV equal to mv square by r, then r equal to mv by bq. Okay. As the force due to the magnetic field acts in the direction at right angle to a direction of motion, the force will only change the direction but will not be able to bring about a change in the magnitude of the velocity. The kinetic energy of the particle will therefore remain unchanged. The force due to the magnetic field will only make the charged particles move along a circular path with the same velocity and therefore the same kinetic energy. Okay. Thank you. And next heading is the motion of positive ions in a parallel electric field and magnetic fields. Okay. Motion of positive ions in parallel electric field and magnetic field. Okay. Motion of positive ions in parallel electric field and magnetic field. Okay. When an electrically neutral atoms losses one or more electrons, when an electrically neutral atoms losses one or more electrons, it becomes a positively charged. Atom and called a positive ions. Okay. When an electrically neutral atom losses one or more electrons, atoms losses one or more electrons, it becomes a positively charged. It becomes a positively charged atom and is called a positive ion. Positive ions. Okay. Okay. Suppose a beam of such positive ions Suppose a beam of positive ions, each of mass m and charge q, each of mass m and charge q. Okay, so suppose a beam of such a positive ions, each of mass m and charge q, moving with a velocity small v, enters a region in which a uniform electric field of intensity, and a uniform magnetic field of induction B are present. Both the field E and B are parallel to each other and are at right angles to the direction of motion of the beam. Okay, right angle at the direction of motion of the beam. In the region of the field, an ion experiences the electric force QE. In the direction of E, and at the same time also experience a magnetic force QVB in the direction perpendicular to the both V and B in the figure. QVB is okay. Initially you can initiate. In the region of the field, ion experience the electric force QE in the direction of E. Electric force QE in the direction of E, and the same time also experience a magnetic force QVB in the direction perpendicular to both V and B, in the figure. QVB is directed out of the plane of the paper. Therefore, during its passage through the field, the deflection of the ion due to electric field is in the y direction, and the deflection due to B in the x direction. Okay, the deflection on the screen are given by SE. The deflection on the screen are given by SE equal to QEI capital L upon MV square, that is SB equal to QBI capital L by MV. Okay, where this is the small l, this is a small n, this is capital L, this is capital L, where L is the length of horizontal path. L is the length of horizontal path, and capital L is the distance of the screen from the center of the field. Capital L is the distance of the screen from the center of the field. Okay, where small is the length of the horizontal path and capital L is the distance of the screen from the center of the field. Okay, then first point is y equal to QE small l capital L upon MV square. This is the equation number first, and x equal to QB small l capital L upon MB. This is the equation number second. To eliminate small b To eliminate small v, we secure v square equation number second, and the dividing by equation number first, we get x square upon y equal to x square upon y equal to q square b square small l capital L whole square upon m square v square into mb square upon q e small l capital L. That we can solve this problem, and we find out I small l capital L b square upon electric field E into q by m, and that therefore x square equal to small l capital L b square by electric field and q by m into y. That is equation number third. That is equation number third, and this is the equation of a parabola. This is the equation of a parabola with its vertex at the origin O of the axis on the screen. The parabola is symmetrical about the y-axis, thus for the constant values of L, capital L and B, and electric field E. Positive ions, okay, having the same charge to mass ratio q by m, but moving with different velocities, will lie on the parabola represented by equation number third. If each ion has a positive charge equal in a magnitude to the electronic charge E, then equation number third is written as x square equal to L capital L B square by electric field and E by m into y, or x square equal to capital C E by m into y. That is equation number 4, where C equal to L capital L B square by E. Okay. Equation number 4 represents again a parabola. The path of traced by a positive charge has parabolic nature. This principle was used by J.J. Thomson. This principle is used by J.J. Thomson, and he determined E by m by using his very famous Thomson parabola method. Thomson parabola method. Okay. Next study, Thomson parabola method. What is the Thomson parabola method? We will be studying about Thomson parabola method in the next study and next day. Okay. Thanks. Now we will go to motion of ions in the